Okay, welcome. Today we're going to look at some application problems involving logarithmic and exponential equations. So go ahead and take your notes out and we'll begin. All right, the first application problem we're going to deal with involves Newton's law of cooling. So I'm going to go ahead and read about that right now. An important application of exponential equations is Newton's law of cooling. This law states that for a cooling substance with the initial temperature T sub 0, the temperature T after T minutes can be modeled by T is equal to the quantity T sub 0 minus T sub R times e to the negative RT power plus T sub R, where T sub R is the surrounding temperature and R is the substance's cooling rate. All right, that is quite a lot of function. That is a function with quite a lot of variables in it. So the first thing I want to do is I want to identify what these variables are. I need to know what T sub 0, T sub R and are going to be. So the first thing I'd like you to do in your notes is, well, write those down. Let's write down the equation and T sub 0, T sub R, and R. And as I read through this, everything is defined for me. What does the function do? What is Newton's law of cooling? That's what T is. What is T equal? T is the temperature after lowercase t minutes. So our big T is like our current temperature after time. So we're going to call that guy the temperature. T sub 0 is the initial temperature. So my initial temperature, the starting out temperature, is going to be denoted by T sub 0. T sub R. What is T sub R? Well, if I read through the function, it tells me T sub R is the surrounding temperature. So how hot it is around the object that is trying to cool. And lastly, R is the substance's cooling rate. How fast does this thing cool off? Okay, we've now identified all the variables, so we can go ahead and start reading our application problem and start filling in the variables that we know, the values of the variables that we know from the problem. So let's go ahead and read the problem. You're driving on a hot day when your car overheats and stops running. It overheats at 280 degrees Fahrenheit and can be driven again at 230 degrees Fahrenheit. If R is equal to 0.0048 and it is 80 degrees Fahrenheit outside, how long in minutes do you have to wait until you can continue driving? So when is that car going to cool off again so we can drive it again? Okay, let's break some stuff down. We've got a lot of numbers up here. First thing I want to identify is, what are they asking us to find? And what they're asking us to find, again, is right here. How long? We're looking for a time. Do I have to wait till my car can continue driving? Okay, so I know my car overheated, and I know I can't drive it again until it reaches 230 degrees Fahrenheit. Okay, I also know my car overheats at 280 degrees Fahrenheit. It has a cooling rate of 0.0048, and it is 80 degrees outside. Okay, I'm going to start with my cooling rate. That's the easiest one to see. That's our R. So our R is going to equal 0.0048. We know our outside temperature, that's the surrounding temperature, is 80 degrees. We know our initial temperature. Okay, our initial temperature is, well, that would be when it overheats. So our initial temperature has to be 280. Okay. So it overheats at 280, so that's going to be our starting point. Now the temperature, we don't want it to get down to 0. We want it to get back to a temperature that we can drive again, and that temperature is 230. So we're looking for our temperature after T minutes being 230 degrees. So how long is it going to take to go from 280 to 230 at this cooling rate when it's this hot outside? Okay, our next step is to simply do a substitution. So we're going to go ahead and write the equation out. T is equal to t sub 0 minus t sub r times e to the negative r t power plus t sub r. We're going to fill in what we know. We know t, we want it to be 230 degrees. So we'll go ahead and drop the degrees off. So we'll go 230 is equal to the quantity of t sub 0, that's 280. That's our starting point. Minus t sub r, and we found that to be 80 degrees, that's our surrounding temperature. Times e to the negative r, which is 0.0048 t, that's our time, plus our t sub r again, our surrounding temperature, which is 80. Okay, with a simple substitution, into Newton's law of cooling, we have this equation, and this is just about simplifying and solving for t. So our first step in simplifying is the parentheses. So 230 is equal to 200 times e to the negative 0.0048t plus 80. And now to solve for t, to get t out of the variable, we've got to isolate the e. We have to isolate e. So I have to get rid of the 80 and the 200. So I'm going to subtract 80 from both sides and then divide by 200. So subtracting 80, 230 minus 80, that's going to be, let's do some quick math, that would be 0. It's going to be 150. 150 is equal to 200. So all I'm doing is doing my simplification. Divide by 200. And let's kind of box this over. Now 150 divided by 200. Let's see, I can cross the zeros out. I can reduce this down. It looks to be about 5 goes into both. That's about 3/4. 3/4. So that's going to be about 0.75. 0.75. So I did the math in my head. If you need a calculator, go ahead and pull it out, because we're going to need one coming up anyway. Okay, so all that work was simply to isolate the e. Now I look at this and I'm going, okay, when I have an exponential, I try to look for equality first. 0.75 in e I can't write to the same base, so I'm going to have to take the logarithm of both sides. Because my base is e, the logarithm base will be e as well. So this is a ln of e to the negative 0.0048t and ln 0.75. These are inverses of each other, so I'm left with negative 0.0048t to the ln 75, and we're just about done. Lastly, divide through by negative 0.0048 on both sides, and this becomes a calculator problem. Okay, remember, ln is in your calculator. You don't need to hit a change of base formula on this. So type in ln of 75, divide it by negative 0.0048, and that will leave an answer of approximately 60. So with t being approximately 60, little t, which is our time, in minutes, we have approximately 60. So for you to drive your car again, when it overheats to 280 degrees, it will take 60 minutes to get back to 230 degrees. Okay, this is a application problem involving Newton's law of cooling. We had to use, it became an exponential. We had to use logarithms to solve. Go ahead and jot down any notes you might have, and we'll answer them during class. Thanks a lot.